Hey, I am Kosisotiku Okafor. This is milestone one of my final year projects. I divided into milestones so I can track my progress. The topic is multi-agent reinforcement learning for adaptive TCP congestion control. TCP, as you all know, is the transmission control protocol on the OSI TCP IP model. Basically, how data transfers from one computer to the other. Okay, so today I'm just going to show the first thing I've used, I just built a basic network simulation that it compares two traditional algorithms, because yeah, there existing two existing algorithms, Reno and Cubic. They are just competing over a shared bottleneck link. So this is just the foundation. Actually, before I touch any ML, any reinforcement learning, any AI stuff, I need to understand how congestion actually works. So I'm just going to walk you through what I did. Okay, here's my script. ns-3. I'm using ns-3 network simulator. It's open source network simulator. Okay, so you can see I have two senders, sender 0, sender 1. Sender 0 uses Reno, sender 1 uses Cubic. Also the receiver 0, receiver 1. Okay, they both connect to router 0. We connect to router 0 on 100 Mbps link, that's the fast ones, and then router 0 connects to router 1 through this bottleneck, only 10 Mbps in comparison to this 100 Mbps. It's this 20 millisecond delay. On the right side, router 1 connects to the two receivers, this one and this other guy here, receiver 0 and receiver 1, receiver 0 and receiver 1. Both senders are trying to push data through the same narrow pipe. That's where the congestion itself happens. The congestion window is not big enough for both of them. So one, we have to bully the other person. That's in the better algorithm, bully the other one. So I also set a DropTail queue on the bottleneck link with only 100 packets there. So that just means that when the queue itself, the packets get dropped. That's exactly what I want to say. Okay, just going to go to my terminal. Okay, I'm just going to run the simulation. Okay, the simulation has started for 60 seconds. Just going to speed that up. The both senders are ready, so they will try to send as much data as possible the whole time. So the simulation is going to produce two files, because I've run it before. We're going to produce two files: the FlowMonitor XML with all the statistics and the NetAnim that for the animation. So I have to visualize it. The animation XML. I'm just going to show you the results. Here I have the throughputs. First throughput, flow 1 is Reno, flow 2 is Cubic, as you all know. Flow 1 Reno, it's got about 4611.3 kilobits per second. Flow 2 is Cubic, it got about 5,330 points. Not about, it got exactly 530.1. Cubic got more bandwidth, so that's because Cubic uses the cubic function to grow its congestion window faster than Reno. Reno zone is a linear increase. After a packet loss, Cubic recovers more aggressively and grabs more of the freed capacity. As I said, it's greedy when the sharing network with other it's algorithms that are less than it. So I'm just going to open the other image I generated, the delay. Now to delay, both flows here, they have about 60, 61, these are approximately 61. Let's just say both of them have approximately 61. You get? So that's like 61 milliseconds. I don't know why didn't I enter this here? 61 milliseconds of delay. The base propagation delay of the bottleneck is only about 20 milliseconds. So the extra 41 milliseconds is the queuing delay. The time packets, they spend time waiting in the router's buffer. That's just the buffer boot. That thing I said I did intentionally. That's it in action. Now for the loss, packet loss. Reno lost just on this line itself 0.02%. Cubic loss 0.0. This is about 0.04, but this is 0.04%. They are both tiny fractions, obviously, but this tells me that the queue was full most of the time. But the algorithms, they backed up before causing any massive drops. Bottleneck was congested, but it did not collapse. Okay, what exactly did I learn from all this? What exactly did I learn? Basically, and I want to see number one thing I learned here is TCP algorithms. They do not share bandwidth equally. As you can see, Cubic got more than Reno just because of how its congestion, its window growth function. The function that makes the congestion window grow for it works differently compared to Reno that is linear. So it has the advantage. Number two, congestion is clearly visible. I can see it in the graph, the extra delay, the loss events, and also in this NetAnim I think I displayed just the stuff movement. Crazy. So this is my baseline. When I later built in my RL agent, that reinforcement learning agent, I'll compare it against these numbers. So I'll know whether can my agent be faster than Cubic. Not faster, fairer. Because faster was supposed to be as greedy as Cubic. It needs to be fairer than Cubic, and can it keep up? Can it keep the delay to be lower? That's what my other milestones are. As I said in the beginning, this is milestone 1, that's milestone 3, 4, 5, that's what they're for. Okay, so this is milestone 1 done. Next I'm going to go deeper, more flows, adding BBR as Google's that bottleneck bandwidth, yada yada. Yeah, algorithm. And I'll measure fairness properly. So thanks for watching if you made it this far. Even though I have been anything wants to be. Okay. All my codes and the results, the graph, I put them in this docu folder. So they're just in my project repository. I'll link everything below. See you in milestone 2.